Have you ever really thought about why a rubber band stretches but a twig just snaps? It all comes down to the secret language of materials. And today, we're going to decode that language and really get to the bottom of what makes our world tick. Let's dive in.
Yeah, it really boils down to this one simple question. Think about it. A steel beam under a lot of pressure will actually bend, right? It gives you a warning sign. But a glass window? It looks perfectly fine 1 second, and the next, it's just a million pieces on the floor. Stick with me, and by the end of this, you'll know exactly why that happens. Okay, so to answer that big question, we kind of have to learn a new language. And just like any other language, we've got to start with the basics. A couple really fundamental words that explain the forces happening and, how materials react to them.
All right, the two most important words you need to know are stress and strain. It's actually pretty simple. Just think of it like this. Stress is the force you're putting on something, the push or the pull. And strain? That's just how much the thing bends or stretches because of that force. It's a basic cause and effect, and it is the key to, well, everything else we're about to talk about. So, how can we actually see this relationship? Well, engineers have this amazing tool called the stress-strain curve. The best way to think about it is like a material's DNA. Seriously. It tells you the entire story of how that material is going to act when you put it under pressure. From the tiniest little push all the way to, well, catastrophic failure. Okay, so let's walk along this curve. At the very beginning, when we apply just a little bit of stress, the material deforms just a little bit. For a while, this relationship is a perfect, predictable, straight line. This part? Oh, engineers absolutely love this zone because it's where the math is easy and it just works. You double the stress, you get exactly double the strain. It's what allows them to make really precise and, more importantly, safe calculations. Right after that straight line, we hit something called the elastic limit. I like to call this the rubber band point. You know how you can stretch a rubber band, let it go, and it snaps right back to its original shape? Well, materials do the exact same thing, but only up to this specific point. And this property is absolutely crucial for things like, say, a bridge that has to flex a little when cars drive over it, and then pop right back into place. But what happens if we keep pushing? What if we go past that elastic limit? That's when we hit the yield point. And this is the point of no return. Think of it as the bent paperclip point. You bend a paperclip just a little, it springs back. But you bend it too far, it stays bent forever. It has been permanently deformed. And that right there is the huge difference between temporary, elastic deformation and permanent, so-called plastic deformation. So we keep pulling on it, and the material fights back. It resists more and more, until it hits its absolute maximum capacity. That peak right at the top of the curve, that's its ultimate strength. For an engineer, this number is everything. They design buildings and bridges so that the normal, everyday stresses are way, way below this point. They build in what's called a factor of safety to make sure disaster doesn't strike. And after that peak, well, it's all downhill from there. The material just can't handle the stress anymore. It starts to weaken and weaken until finally it hits the breaking point. That's it, the end of the line. Complete fracture. The material just snaps. So there you have it. That whole journey we just took along the stress-strain curve, it gives us the exact language we need to classify materials into two, let's call them personalities. And believe it or not, this is how we're going to finally answer that big question we started with. And here it is, the big reveal. This is the answer. A ductile material, like our steel beam, has a really long journey from its yield point to its breaking point. See how it stretches and deforms? It gives you tons of warning that something's wrong. But a brittle material, like our glass window, it has almost zero plastic deformation. It goes straight from elastic to broken in an instant, no warning at all, just poof, a sudden snap. But a material's built-in properties aren't the whole story, not by a long shot. To really understand them, we have to look at how they change over time, because the environment, it can attack them. And the most common, everyday example of this is corrosion, which you probably just call rust. To put it simply, corrosion is really just a material trying to get back to its natural state. You see, most metals aren't just lying around in their pure form out in nature. They're found as ores, mixed up with other stuff like oxygen. So corrosion is basically just the metal trying to return to that more stable original form. It's just chemistry doing its thing. So what is the chemistry of rust? Well, it's basically a tiny electrochemical reaction happening right on the surface.
In the simplest terms, when you have iron atoms and you expose them to both oxygen and water, they start to react. And that reaction creates a totally new substance, that flaky, reddish-brown stuff we all know as rust.
Okay, so here's the really important part. Why is a little bit of rust so incredibly damaging? It's because rust actually takes up more space than the original iron did. So when you have steel rebar inside concrete and it starts to rust, that expanding volume creates this immense pressure and it literally pushes the concrete apart from the inside out. This is called spalling, and it's a huge cause of structural failure. All right, so now that we've got the science down, let's check out how engineers actually use all this knowledge to pick and choose and even combine different materials to build the world all around us.
Just take a look at this. All of these metals are based on iron, but look how a tiny change in the amount of carbon completely changes their properties. A lot of carbon gives you cast iron. It's hard and brittle, but amazing under compression, so it's perfect for things like pipes. Take almost all the carbon out, and you get wrought iron. It's tough and ductile, ideal for something like a crane hook that has to bend without snapping. It really is all about finding the perfect recipe for the job. Then you've got plastics, which are a whole other universal materials. I mean, their advantages are just huge. They're super lightweight, they're great insulators for both heat and electricity, and you can mold them into pretty much any shape you can dream up. Just think about their weight. That one property has totally revolutionized everything from cars and planes, making them way more fuel efficient, to simple packaging, which makes things a lot cheaper to ship.
And just like metals, plastics have their own personalities. You've got thermoplastics, which are kind of like butter. You can melt them down and reshape them over and over, which makes them really easy to recycle. Then you have thermosetting plastics. These are more like cake batter. Once you bake them, that's it. They're set permanently. You can't remelt them, but that's what makes them so fantastic for high heat stuff, like the casing on your electrical plugs. And that brings us full circle right back to glass. What a weird material. It's a total bundle of contradictions. It's incredibly brittle when it's a window pane, right? But a super thin fiber of that same glass can be stronger than steel and carry all of our internet data across the entire ocean. It's hard, it's transparent, it's so chemically stable we store super strong acids in it. Just a truly unique and versatile material.
So, with all these different options, how on earth do you pick the right one for the job? Well, that is the fundamental challenge, the big dilemma for every single designer and engineer out there.
You know, every single man-made object you see is the result of a very specific decision. A coffee cup? It needs to handle heat without shattering. That's a job for ceramic. A huge bridge? It's got to be ductile, but also incredibly strong. That's steel. The story of our engineered world really is the story of these material choices.
And all this knowledge isn't just for building new things. It also helps us fix what's broken. Remember that spalling concrete we talked about? Here's how engineers actually repair it. First, they chip away all the loose, damaged stuff to get down to a solid base. After they clean it all up, they add a steel wire mesh. Now, why do they do that? Well, concrete is great when you squeeze it, but it's terrible when you try to pull it apart. That wire mesh adds the tensile strength that the concrete is missing. Then, a final coat of plaster goes on to seal and protect the whole thing, making it even stronger than it was before. So, we've gone on quite a journey here, haven't we? All the way from simple stress and strain to the complex choices that literally shape our world. Now you know exactly why steel bends and glass shatters. But as we keep pushing the boundaries of science, you have to wonder, what new materials are just waiting out there to be discovered? And maybe more importantly, what incredible things are we going to build with them?